Hello. I hope okay. I restart because I am feeling that most of you missed the presentation.
Now it's okay.
Huh?
Yeah, now it's okay.
And now it's okay. So we were talking about the success and failures of a classical approach to AI. So we have many successes. The example is Google. Recently, we have even Go, which is slightly different from Google from chess because it's a much less structured environment than chess, the Go game environment. And on the other hand, we see that we have problem in building typically robots, so system able to interact in an adaptive and robust way in the real world. If you choose the line, the idea that you should have an emerging behavior in your robots, the first problem that you have is the problem of the symbol grounding, meaning that in most systems following the classical approach to AI, the designer of a system create some object set that can be filled by the house, the door, the dog. So you basically do what is done in this cartoon, in this picture. So you typically label the objects for the AI, and this is also what you do in in the typical reinforcement learning algorithms of deep learning used for recognizing pictures because you use the tags. You need 100,000 pictures of dogs, people tag them, and then the system is able to abstract a very now, I would say in the last couple of years, is able to really recognize static pictures in a very good way. But you have this tagging problem. So you have many people, a crowd of many people, put painting on the picture names, so strings that the system actually doesn't understand. And this is an approach. The approach, which is actually the problem, which is actually um, haunting the emergent paradigm of AI is how we put symbol into the systems. Or so here I use the word symbol anchoring, but single grounding, but it's probably more appropriate to talk about symbol anchoring. So to have, meaning that you have a list of floating strings and you attach the strings to some cluster of data points that you have detected. And also on this, we will come back later. So if we consider these two approaches that I quoted several times, the problem that we have in the first, if you see cognition as computation, the problem is that, for example, is the frame of reference program. If in this second approach that I prefer, but has also its limitation, the problem to is to the sorry, because there is a kind of echo. The problem is given by, I'm trying to fix the, okay, so the problem is given by the necessity to have a complete representation of reality that is sometimes not correct. And now I notice another issue. Because we are losing. So this, so we, okay. Okay, so from time to time, it seems that we lose the synchro, and but okay. So this is the, but so we have, so about the classical approach to AI as problem, also the new one as problem. I would say that if we accept the idea that this is the way to go, these problems are actually interesting research questions. No, so so how we can put at work this idea that the interaction with the environment is always mediated by a body. I was of a problem on that also a typical problem of a classical approach is the frame of reference approach. It's famous, this example of proposed by Herbert Simon on about an ant walking on a beach. So the ant walking on a beach, you can imagine this beach in the picture, where you have many different obstacles. So you have small rocks, bigger rocks, and the ant seems to walk in a very complex way. But not necessarily this complexity of behavior comes from ants, because to have this kind of very messy trajectory on the sand of the beach, it's enough to have simple behavioral rules. So just move away from a rock, and if you have to go around it. If a beach is complex enough, the trajectory of a ant will be complex, but this is not necessarily due to the complexity of a brain of a ant. And so this is something which is called stigmergy. So it's the effect of the environment, the contribution of the environment to the behavior of a system. What I was saying is that considering this aspect of a symbol grounding, on how to model morphological computation, how to model the embodiment, are all questions which have, are all things that from an intuitive and qualitative point of view seems very natural. But if you want to implement them, you basically need to develop a new set of mathematical models for control, for behaviors, for representation, whatever you want to call it. Because symbols are useful because they allow to have a short planning procedures, for example. If you don't have symbols, you have to consider a huge amount of data points. So it's while the symbols that we refer to usually, like triangle, square, cubes, are probably the endpoint of a cultural evolution. Some kind of high-level representation of the world is probably present in not only in our minds, representation between commas, within commas, but something like that has to exist for efficiency reason. Anyway, in this case, the Foyt experiment, think of the ant bigger by 1,000 times. The working patterns will be completely different. So we have this situation. On the one hand, we have robots, which are a very accurate, repeatable, precise movement. And on the other side, we have humans who are designed, are low precision, compliant, reactive more than planned, and able to cope with uncertainty. Simon Hens was actually studying reality by Hulk Cruz, looking at how ants work. And what has been discovered is that actually the working of an ant comes from the emergent behavior of a very simple control of a single line. And this behavior is actually mediated by the body. How to model that? That's an interesting mathematical issue. In one of the next, in the next lecture, both me and the guest lecturer will show you how exotic those models could become. This is a famous example by Fumiya Ida of morphological computation. And the nice thing is that this puppy, which was extremely simple, was able to work, to run of a treadmill in a very natural way. I will, and this is taken from a 10 years old science paper by Ralph Pfeiffer and others. You see that if you want a complete model of a controlled robot, we should look for something like what we see now in the picture. So we have a controller, but then a lot of behaviors are a direct consequence of a musculoskeletal system and of a task and the environment. So think to the ant working on the beach and also the ant studied by Hulk Cruz. So there have been attempts, I don't have time, but if you are interested, we can go into this offline or in a specific lecture. Essentially, this puppy is following some attractor in his own dynamics, which are the consequence of the body structure of a puppy. This is extremely, so it's interesting because you know where is the problem. The problem is that if I want to build a demo, I build this puppy, or I build the biped passive walker, and I'm okay. If I want to exploit this principle in a robot doing some purposeful task, I need to develop not anymore from scratch, but from an early point, a mathematical modeling framework to do that. Despite the fact that, as told, the principle seem very, very compelling. Now, I don't know, I will skip this. Oh God. I will try to I'm doing this experiment. I hope it will work. I want to show you two things actually. One, but briefly. One, I'm not going to show you the whole movie. One is the extreme complexity of emerging from simple rules like keep a constant or almost constant distance from your neighbor, which is what we typically see in swarms and was studied, proposed initially by Reynolds for computer graphics to be able to simulate in computer graphics this kind of behaviors. And then now we wait for the ad. And this is what I anticipated you already. So this is a study made. So a study was a video commissioned by Harvard, more or less summarizing what it is known about the inner behavior of a cell. I mean, even if we don't have a clear understanding of how to implement this kind of behaviors, I think that it is intuitive, from an intuitive standpoint, it's clear that it is the approach is not ours. And so it's a serious challenge to implement this. As I told, we will come on this next time, next lecture, we will go a bit more deeper into this issue. Now I want just, since we are slightly late, I want to quote this important aspect that is, now it is less, but in the past it has been more neglected when studying intelligence. Because if we look, you know that at least at the beginning, the idea of AI was to replicate. So still, if from time to time you hear someone talking about human level intelligence or even super intelligence putting at risk humankind. Personally, I think we are quite far from those kind of risks, but from a poor conceptual standpoint, we can see that in human-like, the real human level intelligence comes from a number of different processes, call them, if you want, optimization processes or selection processes of behaviors at different levels. Because we have the phylogenetic level, which is evolution of a species, and where something is set. Then we have the ontogenetic level, which means is the development. So when you think about grasping, for example, next lecture in a few minutes, because we are going a bit late, will be about grasping. In humans, I think I told that, I used to tell that many times, but this arm is able to perform some relatively sophisticated grasping task, but it took about 2 years to reach a level where the arm was a small arm similar to this. The brain structure and the symbolic structures developed together. So if you remember the last lecture from Josh Bongard, we have reason to think that development is necessary to make evolution quicker, so to speak. So, and this is it. And then we have what probably is we are now able to implement, which is what is just one step of evolution of human level intelligence in humans, but also of cat level intelligence in cats, or octopus level intelligence in octopus. So it's the year now. So it's the short-term optimization of a behavior, which you can see as a so it's typically more, can be learning. And what is now very successful is, I hope we will have time to come back. This in the, I would say, the last lecture is basically deep reinforcement learning. So deep reinforcement learning is a a very data hungry approach to what we may call the here and now. So it's the final optimization. And it relies on tagging. So it's still not, but this is the reason why I'm not so worried by AI taking control of the world. I think AI is still very, very, very limited in the area. Nice to notice that Turing, in a paper from the 50s, actually was well aware of the importance of learning and development in the developing of human level intelligence. So I think that we may leave some more sophisticated consideration for future lecture, and I want to finish here just to show you how the timescales affect the development of human-like intelligence, or if you want, of baby-like intelligence, which is still more than what has been implemented in robots. So you have a level, and you see also the many levels involved, because you have the neurons and the neuromodulators in the neurons. I leave aside the idea of Roger Penrose that we may also have a quantum level. So let's assume that it is not needed. And then we have neural oscillators. And then we have other things that are already emerged, more complex structures, but I think of them like clouds or rivers in the data, which are emotion, moods, and then symbols or proto-symbols or other forms of coupling. So since I think I went about 10 minutes out, I think we can leave questions and answers for my part out, and I leave the floor to Nicolas Rojas from the Imperial College, who will again show you a nice and I think I find a very interesting approach to manipulation. We are actually the mechanical part as a role. We have to work more of this, but I think it's what is going to show is very, very, very interesting. So enjoy. Nicolas, the floor is yours.
Thank you. Okay. Hello, everyone. I'm very glad to have the opportunity to talk to you today. Just to thank Fabio for the invitation. Fabio this week here with us, and we are very happy of having him here. So I'm going to talk about enhancing in-hand manipulation via mechanical intelligence. This is one of the main topics of my research group. I am Nicolas. I am a lecturer in the Dyson School of Design Engineering, Imperial College London, where I lead the REDS lab. So initially, I will talk about general manipulation and how we see manipulation in my research group, so you can have a better perspective of what we are developing, and later I will focus more on the aspects that we have started or we have explored in the last year, and will give drive our our research agenda for the coming ones. So manipulation is for me is basically the future of robotics. So far, robotics has focused mostly on mobility, and we have progressed a lot in these aspects. And the coming revolution is manipulation, and I consider manipulation is the technology that makes that departs robotics from any other technology. So manipulation is a very broad word, and sometimes these broad words are difficult to be defined. But basically, manipulation is the involvement of technology to
Good. Oh, oh, okay. Sorry. Okay. Can you hear me right now? Okay. Okay, perfect. So I was describing about the classification about manipulation and the difference between gross and fat manipulation is how we see this in my research group. So gross manipulation is the coordination of these large body parts and movements, and basically corresponds to the different behavior that we can have from extremities, from limbs. It's important here, as I was describing, that this type of activity that we can do with that with gross manipulation can be precise or can be rough. So, for instance, when we need to hammer, for example, in the picture here, uh, there is part of that activity that is very rough, is very large in the motion, but at the very end you need a very precise control to be able to hammer the what you want in the position that you like. So the second part is fine manipulation, and usually we associate this with hands, okay, with fingers. So basically the coordination of small body parts and movements. So this includes the motion of fingers, the motion of wrists, and of course in general of the hand. And there are multiple examples of this. So from playing piano to writing and other things. And here again, we can have precise motions or more rough motions. Okay, so in my research group, that is the REDS lab, is the Robotic Manipulation Engineering Design and Science Laboratory. We focus on the analysis, design, and implementation of robotic systems that can purposefully perform physical changes to the world around us. So we have uh, two broad research interests in gross manipulation, in robotic gross manipulation, and in robotic fine manipulation. So basically, we focus a lot in conceiving new types or manipulators and end effectors, new concepts and new technologies. And basically, we follow a theoretical and a practical approach. We are interested in investigating what can be built from the laws of mathematics and nature, and 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 to obtain manipulators and end effectors from these mathematical models, and that can improve the state of the art. But one very important part of our research is the practical aspect. So we build robots, we build things from scratch. We need to test the things because in manipulation, from my perspective, you can have multiple simulations and everything, but the real world is different, and we have to deal with that, and we have to develop robot hardware that is able to be reliable to the uncertainties of not just the environment, but also the uncertainties that come from the robot itself, from the sensor, from the actuators, and so on. So our long-term goal is to create robots from scratch that surpass the manipulation capabilities of certain humans and other animals and their diversity and uncertainty. We have multiple research areas right now, and in this talk, I'm going to focus mostly in 4 of these aspects that we are working right now. So I'm going to talk about quantum modeling and characterization, of course, about gesture manipulation, about in-hand manipulation, analysis, and planning, and about the design of mechanically intelligent robot manipulators and hands, and particularly now I'm going to focus on hands. Okay, I'm going to start talking about underactuated hands and basically how we can leverage this technology to improve the gesture manipulation of robotic hands in general. So underactuated hands and underactuated fingers can produce passively adaptive graphs with minimal control and hardware complexity. So this has been a very successful approach and has allowed us to develop to grasp objects with minimal control needs and very reliable. So there are multiple examples of those technologies. Here we see the video of one of these robot hands performing multiple graphs. But the thing is that gesture manipulation remains a very difficult task, not just for underactuated hands, that are the hands that, from my point of view, have mastered how to grasp objects, how to grasp irregular objects with a very simple approach. Of course, stand grasping to gesture manipulation for this hand is difficult, but it's also very difficult or even more complex for redundant actuated hands. So the question here is what we can do to improve these limitations. So to put the things in context, in-hand manipulation is basically the extension of the utility of hands beyond just acquiring and maintaining grasp. So we want to grasp an object, and from grasping that object, we want to modify the location of the object, okay, the position and the orientation of the object in order to perform another activity. Okay, so we are going beyond just grasping. So the solutions for enhancing in-hand manipulation capabilities can be broadly classified as extrinsic dexterity and intrinsic dexterity. So extrinsic dexterity corresponds to these approaches that use resources extrinsic to the hand, for example, a table or gravity, because gravity is something that is external to the hand, in order to improve or to facilitate the manipulation that you want to perform. Examples of this extrinsic dexterity approach include in-hand grasping and cage manipulation, because you use gravity for improving that. So there are several researchers that have been made important advances in this area, and basically one of the important aspects here in extrinsic dexterity and in general the approach that we want to follow here is that we want to make things that are reliable in open loop first. So things that can control the object, manipulate the object in open loop, because our hypothesis is that if we develop the best open loop hardware that is very reliable, later when you close the loop with any type of technology that you want to follow, so classical control or machine learning approaches, your results should be better. So in extrinsic dexterity, we have seen some examples of multiple manipulations, like the flip, the pitch and flip task of a coin, or for instance, the reorientation of cylinders, and so on. And here you see that you are using external features to the hand in order to, accomplish these activities. In intrinsic dexterity, the manipulation of an object is achieved by applying forces to the object through the fingertips. Okay, so we grasp the object and we just rely on the forces that we can exert from the fingers in order to change the orientation of the object. So this is the typical definition of what we call dexter manipulation. So in this area, there have been three main approaches to improve or to enhance the hand manipulation capabilities of our hands. One is, of course, the use of high fidelity contact sensors to close the loop and try to manipulate the things easier. Another very successful approach has been the use of active or sliding surfaces on the fingertips. And another approach is that you grasp the object, you explore the word space of the object, and now that you know the word space of the object, of what is called the dexter word space, you can propose planning algorithms. So I want to focus a bit in the second aspect about active and sliding fingertips, because it has been successful. So basically it corresponds that you add some kind of actuator, and a slider actuator or a rotator actuator in your fingertips, and you basically can, in that way, can control the object. Of course, the results are good, but we are more interested in understanding better how we can perform these activities directly from the forces of the fingertips. And one of the reasons is because one of the problems with active surfaces is that you, in the end, deal with the problem of controlling the cooperation between these new actuators. So you have the actuators of your hand plus the actuators of the fingertips, and the coordination of these things in order to perform the activity is not necessarily straightforward. So our approach is a new intrinsic dexterity approach that is based on the use of flexible and adaptive mechanical components that generate predictable behaviors of the hand object system. And this is our main difference and how we depart from previous approaches. So basically, we see the object and the hand as a whole system, and from there we evaluate how that system can behave and what we can do in order to obtain different motions that could be useful for the object. So the three aspects that we have focused or we have studied for reaching this or pursuing this approach have been contact modeling, manipulation analysis, and design of robot hands. I'm going to briefly talk about them and what we have done so far about that. So I want to start talking about contact modeling. So the type of contact interactions which can occur between a grasp object and a fingertip are usually classified in 9 categories. So the first category is, of course, there's no contact. So the object has 6 degrees of freedom. And the other contact characterization that we have are point contact with friction, line contact without friction, point contact with friction, planar contact without friction, and so on. And here I indicating the number of degrees of freedom that we have with these typical or standard contacts or models of interaction between an object and a fingertip. So the classical or the more useful contact characterization or contact models that we have in robotic manipulation are point contact without friction, point contact with friction, and soft finger. And this is the case because basically these contacts are useful for arbitrary objects. It means that there is no an assumption of how is the geometry of the object. This is true for point contact with friction and soft finger, but it's not true for point contact without friction. But it is traditionally have been included in this set. But actually, the only 2 of those has indeed this characteristic. So with this, I would like to talk about kinematic equivalence of these contact models. Okay. A kinematic equivalent is simply a single kinematic constraint that represents the constraint motion between the two contacted bodies, between the fingertip of the object. That's a kinematic equivalent. It's a single kinematic constraint that describes these two things, and this interaction, sorry. So we have our three standard contact models, that is point contact with friction, point contact with friction, and soft finger. So the kinematic equivalent of these contact models are, in the case of point contact with friction, is an spherical plus a planar joint. In the case of point contact with friction, is a spherical joint. And in the case of the soft finger, is a universal joint. And here we are just showing the different characterizations or kinematic equivalents of the standard contact models that we have. So a very interesting aspect is that this relation between the contact models and the kinematic equivalents is indeed the opposite. How in robotic manipulation we develop the concept of contact models was first that we thought, okay, historically how this was done was, let's model the connection between the fingertip and the object as a kinematic pair. That was the origin of the contact models. And after that assumption, we lead to the development of the contact models, and this was introduced by Salisbury in his PhD thesis, and it was also complemented by others later. So, as I was saying, all standard contact models using robotic manipulation are based on modeling the effects of a fingertip contacting a body as a kinematic pair. So when we realized about that, we started to think, okay, why if we can have a more general action of this interaction between the object and the fingertip, and we can probably have a more richer definition of contact models. So the natural generalization of the standard action of using kinematic pairs is to use kinematic change. So that was the natural generalization, and we started to explore that, and we started to explore how we can model the interaction between the fingertip and the object using kinematic change. So we have proposed this kinematic chain-based contact model. This contact model is based on what we call an extension of the Bruinig-Hund approach of surface-surface contact. Here, this represent the boundary of the fingertip, and this of here represent the boundary of the object. And this model is made of serially connected revolute joints, where these two revolute joints of here corresponds to are located in the curvatures and the center of curvatures of the fingertip and the center of curvature of the object. And here we have a revolute joint across the point of contact. We are in this model. We model friction using what we call resistant passive joints, and we are locating these resistant passive joints in the fingertip. A resistant passive joint is basically, usually passive joints are modeled in a way that they move as soon as you exert any torque on the joint. We model friction by saying that in the fingertip, these three joints are resistant passive joints. It means that they can resist motion till some threshold, and when that threshold is passed, so it breaks the contact, because basically the friction eliminates that. We have opted to call these resistant passive joints instead of friction passive joints, in order to avoid implications of the geometry of these joints, because and the nature of the phenomenon. So basically, we just say resistant passive joints are those that can resist motion till some point of the till some torque. So thanks to this generalization, we have proposed a general classification of contact types. And basically, we classify four big contact types of this. Here, just we have some particular cases, special cases. And important is that all standard categories using robotic manipulation, this is the Salisbury taxonomy, including line-line contact with friction that was introduced later by Hunt, that was in the mid-90s, are obtained as special cases of this generalization. And moreover, we have proposed new contact models from this generalization that are useful. Here, I'm not going to go into detail, but we can prove, or we have shown that how the assumption of your contact model can lead to wrong results of your analysis. And for that reason, it's important to have a larger classification of contact in order to try to mimic better reality. So with this, I'm going to talk about manipulation analysis. So this has been our first approach, our first goal to enhance manipulation. So in manipulation analysis, we have focused in what is called, or what we call precision manipulation, okay? In precision manipulation, we define precision manipulation as when a grass object is repositioned within the hardware space without breaking or changing the assumed contact model, okay? So, and this is very important because any time that you analyze manipulation, you are assuming some kind of contact. Okay? And in precision manipulation, we say, okay, it happens when we can manipulate the object without breaking or changing the assumed contact. So example of this manipulation include writing, include opening a door with a key, include using a scissors. So there are multiple applications of this kind of manipulations. So imagine that we have this three-finger hand. This three-finger hand is a very popular layout. It's the same layout that we have in several commercial robot hands. Our goal with this analysis is to determine the feasible movements to reposition any grass object within the hardware space without breaking or changing content, of course. And most importantly, we want to define which of these possible displacement can actually be controlled by the hand actuators without depending on external factors to the hand, for example, gravity or other things. So we want to understand really what is the motion of the object that we can control with the hand actuators. We call this precision manipulation analysis, and we have developed this during the last several years. So one of the important things of precision manipulation analysis is that in general it's impossible to do with the standard techniques for grasping analysis that we have. It's very difficult. It's in general not possible. So for that reason, we started to explore how we can do that, how we can characterize the motion of the object first, and later how we can determine what actually are the displacement that we can control of this object with the actuators that we have. So our method is based on the kinematic analysis of the closed kinematic chains associated to the hand object system. So imagine that we have this two-finger hand with opposed revolute fingers, so two opposed thumbs, basically, a very simple hand. So the first step is we model the contact between the fingertips of the object using the kinematic equivalence that we have introduced previously with the contact modeling that we have introduced. So for example, we can use point contact without friction, or point contact with friction, or tubular contact, or whatever you consider, depending also on the design of your fingertips, or for instance. The second step is we translate the hand object system into a closed kinematic chain, and we determine its mobility. And the third here, so for example, in the case of these two finger, two revolute fingers hand, we model the contacts with contact with friction. So the associated hand object system in this case correspond to a closed kinematic chain that is a 6-bar linkage with two RRS serial limbs, revolute, revolute, and spherical limbs. And the resulting mobility in this case is 4. So once we have this model, we construct the corresponding graph of kinematic constraints here. So we see the example of this construction of this graph of the kinematic constraints. So basically, we are describing how the constraint between the object and the link, and between this object and the link, between this link and this link. So we describe that characterization of the kinematic constraints, and we reduce this graph using Herbig's group theoretic approach to obtain actually what are the feasible displacement that we can control of the object. So in this case, for this very simple and basic example, the characterization of the displacement of this object of here corresponds to a composition of planar motions and a rotation around the contact points. That is the characterization of the motion that are possible with this hand for any object. So after these 4 steps, we obtain a definition of the general displacement characteristics of any grass object relative to the palm. Finally, what we want to do is to determine which of these displacement can actually be controlled by the hand actuators. And to this end, what we do, we repeat the analysis, but we log the actuators that we have. So in this case, on the hand, we have 4 actuators in general. Okay, so each for each of the joint that corresponds to the joint of the fingers. So if we run this analysis with these log actuators, we obtain that for the case of this hand of here, this motion of here, the revolution are along the axis defined by the contact points. So this of here means that basically there's a rotation along this axis defined by the contact points cannot be controlled by the hand actuators and depends on the external factors to the hand. This is actually very intuitive. We can see this very easily. The issue here is that first, with this method, we can actually compute this kind of thing for different types of layouts, even indeed for any type of layout. And most importantly, we can actually understand what are the motion that we cannot control. This has implication in design, of course, and also for the control of the hand. Finally, I want to finish describing some of the design of robot hands to improve the hand manipulation capability that we have right now, following these ideas that we have introduced. I'm going to present three types of hands. It's one of the spherical hands, the GR2 gripper, and the coalesce topology. So the spherical hands are a series of underactuated 3-finger hand topologies that have 2 curved fingers and a normal thumb, okay? And the main characteristic of this hand is that when you grasp the object, any object has always an instantaneous center of rotation that is fixed and is always at some point relative to the palm. So basically, the motion of the object is always spherical. We think that this can be useful for facilitating the planning of the motion of the object. So for that reason, we explore that. So here we have 3-finger hand, 2 of the fingers are curved, and we have a thumb. So in general, in the first iteration, that was this one up here, we have these two curved fingers and an additional thumb. And basically, using the technique that we have introduced, we prove that the spherical motion of the object, regardless the characteristic of the object, so regardless the characteristic of the object, always the gross motion of the object is spherical. Of course, the specific particularities of that motion depends on the characteristics of the hand and the object, but in general, always the motion will be spherical. And we explore different kind of tool design. So we explore a tooling with a static base that correspond to this one of here. So it's a typical two revolute joints here. We introduce also a pivot here in the thumb in order to enlarge the workspace. And in this case, we have the pivot without the additional without the additional distal joint. So, for instance, in the case of the tool link, this one of here corresponds on the tool link to revolute joint with pivot joint. The extra pivot joint is controlled passively. So we added these elastic elements there in order to have the control of that passive joint without actually controlling that. And we also explored. This is an example of the curved fingers that we propose and a comparison with the normal fingers. And we also propose multiple fingertip designs in order to improve the assumption, because in the assumption of this hand, we were assuming in the design of this hand, we were always assuming that the contact between the hand and the object was a point contact with friction. So as we know that the kinematic equivalent of point contact with friction is a spherical joint, what we try is to mimic as better as possible the behavior of the spherical joint. So to that end, we developed multiple fingertips with a magnetic sphere there, and we cast the urethane of the corresponding to the fingertip in order to have a better performance. So we test this hand with different objects and compare the things, the behavior of the hand, also showing that it keeps the grasping operation. So we are not removing the grasping operation from the hand. Okay. I'm going to check my time here. So here we see an example. This is okay. Okay. Here we see an example of the video that we prepared for that. Here we see the limited in hand manipulation capabilities of underactuated hands. So they are very good to grasp, but the motion are very limited. Here it is very important to highlight that the workspace of precision manipulation is indeed very small, and we will see that. And it's very small because by assumption we cannot break contact. Okay, so this kind of motion are for the reason I call precision manipulation, and very useful for precise tasks. So you cannot expect to have a very large workspace. But that said, the workspace that we have with the classical standard hands is not very good. For that reason, we started to explore how we can do that. So here we see we first run several experiments to prove the spherical motion of the hand. So we do that basically attaching magnets to the object in order to explore the different to show how we was the workspace of the hand. Here we see the example of the hand with the standard fingers. And we did that with different objects. So here we will see how it is the behavior in the case of the spherical fingers of the curved fingers, and in this case there is no a pivot on at the thumb, so the workspace is limited. Here we see the final solution that I think was the best was to add this pivot there with this elastic element, basically in a way that when the forces are exerted to the object, the tool can respond to that forces by lending towards the size that is required, and of course you have a larger workspace. Of course, we will see that one thing is that if theory and reality is a different thing, because when you manipulate an object, you don't have these fixed constraints. But even that, we were able to obtain a better workspace. Here we see the the fingertips, how were designed basically. So we see the magnets, and basically this icosahedron here was proposed in a way that it like cage the object. And we also propose other types of fingertips. So I'm going to advance. We are almost done with this video, so let's try to finish this. Yeah, here basically this is an example. So if you remember the first video of the underactuated hand, this is a small, but the one was even smaller. Okay, so the change, as this is very small, any change here have a big impact in percentage. So that's important aspect. So the second hand I want to discuss today is the GR2 gripper. The GR2 gripper is an underactuated hand for open loop in-hand planar manipulation. So it is called the GR2 gripper because it means the grasp reposition reorient gripper. It corresponds to a two-finger gripper topology that enables and enhances predefined in-hand manipulation primitive. This in-hand manipulation primitive is the reorientation of the object. Basically, that is the planar reorientation of the object, and this enhancement is achieved or is possible for any kind of object. Okay, so why we wanted this? Why we wanted this to do this? Because single degree of freedom two-finger robot grippers are the most common gripper in industry and in research settings. And this is the reason, because it's mechanical simple, is reliable, is low cost, have very good force capabilities. However, they can be limited, very limited outside of pick and place operations. A typical example of this limitation is the alignment of parts before assembly processes. So for example, the pegging in hole alignment task. Okay, that is the type of limitation that you have with these kind of grippers, and you have to rely on the dexterity of your arm rather than the dexterity of your hand in order to perform this activity. This is a generic instance of a traditional two-finger robot gripper with 4-bar linkage fingers. This robot gripper is the most popular one. Here we have some examples, some images that I taken from Google. And the most important thing here is that this gripper, this mechanism has been historically employed solely for grasping operation without considering any feasible capacity of dexterity. So just to grasp, nothing else. For that reason, we started to talk about that, how we can maintain the simplicity of this gripper just to grasp, but let's add some kind of dexterity to this gripper in order to do something else beyond grasping operation. And for that reason, we propose what is called the GR2 gripper. Then the GR2 gripper, we also have this pivot in the palm that have these elastic elements, and we have a reconfigurable palm that allow us to improve the workspace. So one of the differences of the GR2 gripper is that previously proposed designs independently incorporate elastic elements in each finger. In the GR2 gripper, these elastic elements are coupled between these fingers in order to change the behavior of the palm. I'm checking the time because I have to go. Yeah. So as I was mentioning, I'm going through a bit quicker. So basically, in the GR2 gripper, when the GR2 gripper is going to grasp an object, it behaves as a traditional gripper. It behaves as a traditional gripper, just as a normal gripper that you close the fingers. And when you grasp the object, we have shown that when you grasp the object, you always can detect a thrust inside this object in that system. And for that reason, regardless of the condition of the elastic elements, that your grasp is guaranteed, geometrically speaking. So when we have dextro manipulation, and how we propose the dextro manipulation in this case is we propose a hybrid control approach where we have a pushing finger and an opposing finger. And the pushing finger is controlled using position control, and the opposing finger is controlled using torque control. Basically, during these in-hand manipulation tasks, the PAN behaves as a reconfigurable linkage. So we have some examples of this is the traditional gripper, and the traditional gripper, we showed that the traditional gripper can have some kind of dexterous manipulation. So basically we're having a pushing finger and an opposing finger, just that. But here we show that by adding these elastic elements, we can have we can improve that behavior. This is basically the behavior of the GR2 gripper. Here we have here the third example, for instance, with this circle, where we show the behavior of the traditional hand that have been classically used just for grasping operations, and here we see the behavior of the GR2 gripper. This is all of this is open loop, is controlling open loop, is just the result of the improvement of the mechanical aspect of the hand. Okay, so we have recently used this hand for model free hand manipulation, and this is one of the important aspects of this kind of research, because as we know that we can obtain a better range of orientation with the GR2 gripper using a very simple low-level control scheme that is pushing and opposing, and pushing in positional control and opposing with torque control. We have developed along with some collaborators the control of this behavior using tactile fingers, tactile sensors. Finally, I would like to talk about the coalesced topology. The coalesced topology is a result of an optimization of the GR2 gripper. So we started to explore how we can improve this range of orientation of the GR2 gripper. And finally, we obtained this new topology. This new topology is basically a result of a cascade optimization approach, where we were able to show that if we eliminate the palm, in this case, and we have a single joint there, so basically we are obtaining a new topology, because in terms of the topology of the resulting hand is different, we can get up to 90 degrees of reorientation and without any kind of control. We are just using here open loop control. So basically that. Yeah, with this, I think I would like to finish. So thank you very much for your attention. And please feel free to contact me if I can be of any help. And thank you again, Payo, for this invitation. Okay, thank you. Goodbye. Okay.
Okay, I think you have seen the interest of this approach, because actually it's an active attempt to exploit the passivity and elasticity and compliance and the mechanical design to ease manipulation. I think we also see that it is, so there is a lot of work to do, but as researchers, we are very happy. Nicolas is happy to have decades of work in front of him. We are happy. You should be, the students in particular should be even more happy, because we have a constant flow of problems to solve, and this is what we are here for. I don't know if it can take maybe just one question.
Oh, okay, sorry.
Yes, I can hear.
Yeah.
I can.
If you have a question, otherwise feel free to contact me or Nicolas directly, and we will.
No, if there is a question, I'm happy to respond. If no, just by.
So if you have a quick question, because he has a class, I think, in not a long time frame. So if, okay, I don't. So if you have a question, just use the chat, which is safer. But I see there are no questions, so Thank you,
Great.
Nicolas, for your inspiring talk. I've seen, by the way, I have seen myself in many areas of, so I already checked what he was doing, but I have been more and more convinced that his work is very interesting.
Okay, thank you. Thank you very much,
Okay,
Fabio. See you
thank you,
later.
Nicolas. See you later.
I look for you at noon.
Yeah, yeah, yeah.
Perfect.
See you. So now the next speaker is Francesco Corrucci, who I invite to share his presentation.
Everybody, can you hear me?
And so say something. Say something.
Can you hear me?
Yes, now we can.
Perfect. Okay.
Yeah,
Hi,
we
everybody.
are tightening the procedures, so we have introduced this check of sound when the speaker starts. So,
So,
okay.
can you also see my presentation right now?
Yes, you should put it in present. So we should. Okay, now it's perfect.
All right.
As anticipated, this Francesco's talk will be a perfect complement to Josh Bongart's guest lecture on the first lecture. But I leave the floor to Francesco.
All right. Thank you, Fabio, and thanks for having me. So the title of this presentation is going to be Evolutionary Developmental Soft Robotics. And you have seen already some of these in Josh Bongart's talk. As some of you know, we also happen to collaborate quite a lot, so there's going to be some overlap. But hopefully it's going to be useful to reinforce some concepts and also show
Exactly.
some different application scenarios.
Exactly.
All right, so let's start from the motivations of this research. That basically starts from a profound fascination and curiosity for the natural world, and particularly for two aspects. The first one is this explosion of diversity, complexity, and sophistication that we see all across the biological realm, and the videos that you see here are good representatives of that. The second aspect is related instead to the emergence of intelligent and adaptive behavior, as found in animals such as the cuttlefish that you see here with his amazing camouflage skills, or in the creativity of this tiny pufferfish, which is kind of an artist in creating sound words in order to impress the female during the mating ritual. To, of course, higher levels of reasoning and cognition, and as found in humans. So being an engineer, confronted with all of this, the question has always been, can we automatically design a wealth of artificial systems that are as sophisticated, as adaptive, as robust, as intelligent? And can we do so for a wide variety of tasks and environments? This is particularly important in light of the fact that state-of-the-art robots still lack many of these features, and as a consequence, they keep failing outside controlled environments. That is where they're most needed, actually. So one possible approach to this is the biorobotics approach. And what researchers in biorobotics do is to take direct inspiration from nature and try and understand some underlying principles behind the effective operation of some biological creatures, and later applying this insight to the development of robotic artifacts. Soft robotics is one example of that, and what the researcher stole, so to speak, from nature in this case, is the idea that it is useful, it is beneficial to have some kind of deformability and to have soft tissues within both biological and artificial bodies. But if we analyze biorobotics from a critical perspective, we can find some pros, but also some cons. So among the pros, we can list the fact that it usually generates new technologies and new design principles. It sometimes generates new knowledge related to the biological model and insights related to the intelligence of particular species. But also, it requires a lot of human knowledge and careful engineering. It usually focuses on very specific organisms or behaviors, and it is not clear whether it can help us generalizing to arbitrary tasks and environments, and does help realizing general forms of artificial intelligence. So maybe we need something more. So if we take a step back and we have a look at all of these examples that we've seen before, we can ask, what do all these things have in common? And what they do have in common is the fact that they are the result of an evolutionary process. So this entails kind of a paradigm shift in bioinspiration. Instead of replicating some of the solutions found by nature, which is what we usually do in robotics, why not imitating nature's approach to design instead? And that would be imitating evolution. So from replicating natural products to replicating the processes that gave rise to them. And this, to me, is the ultimate form of bioinspiration. So very quickly, let's have a look at the ingredients of evolution. And first of all, in evolution, we need a way to encode the observable traits of an organism, that would be the phenotype, into a compact set of instructions, which would be the genotype or the blueprint of an organism. Then we're going to need a population of diverse individuals, which can reproduce among themselves. And then we need mechanisms to manipulate the genetic materials upon reproduction, and that will be operators of genetic recombination and mutation. Given that these operators are usually error-prone, this introduces random variation in the population and thus novel traits. The last ingredient that we need is a selection criterion. For example, at each generation, individuals that are better adapted to the environment, and this is the concept of fitness, are going to have higher chance of surviving or reproducing, and thus propagating their genetic materials and their traits to subsequent generations. So evolution is a pretty complicated phenomenon, but at the core there is a very simple and elegant algorithmic principle. That is, evolution is a trial and error procedure in which innovation is driven by the random selection of random variations. And yet, the simple algorithmic principles was able to give rise to all this sophistication and complexity that we see in the natural world. So, of course, the researchers have tried to distill and condense these principles in algorithms. And so we have evolutionary algorithms that are population-based, iterative, stochastic optimization algorithms inspired by natural evolution. So what they usually do is to start from an initialization phase where random candidate solutions are being generated. We usually evaluate them through a fitness function that captures the notion of fitness, that is basically a function to be maximized or minimized. Then what we do is to select with higher probability individuals that have higher fitness, and those are going to reproduce. We're going to apply stochastic mutations or recombinations to them in order to introduce variation, and we keep iterating this way until good solutions are found. This can be applied in robotics, and this is what is called the evolutionary robotics field, or EvoRobo. So for example, you might have a population of robots, in this case virtual robots here, and you might want them to learn how to walk. What you can do is to evolve controllers for these robots. So you start with a bunch of random controllers at first, and what you see is that most of the robots are not going to move at all, but some of them, in presence of this random controller, are going to have some motion, like this one that you see over here. So what you do is to select those that happen to move a little bit by chance, mutate them, make randomly mutated copies of themselves. And if you happen to do this long enough, you can end up having robots that actually move quite a lot in this virtual space. So there are some implications to this approach. The first one I'd like to present is the fact that it is in fact a design automation technique. So what you input into the system is a problem formulation in the form of an encoding and a task environment. You input the desired outcome in the form of a fitness function, and what you end up with is a complete optimized robotic system ready to be deployed. This is easier in virtual environments, but with advances in fabrication techniques, we can envision this kind of fabrication pipeline, design a fabrication pipeline also in the real world at some point. Another implication that is relevant to this to the topics that are being discussed in the Shanghai lectures is the idea of coevolution. So in evolutionary robotics, evolutionary algorithms are usually coupled with powerful encodings, which allow to represent basically all the complex characteristics of a robot, and thus to co-evolve and co-optimize them. So for example, you can co-evolve morphology, controller, sensory system, basically everything that you can possibly think of. And this is particularly important in light of the concepts that we find in embodied cognition that tells us that intelligent and adaptive behavior starts within the body and its dynamic interplay with the brain and the environment. That would be the concept of embodiment. And also that a suitable morphology can greatly simplify control by performing implicit or explicit morphological computation. So the idea of co-optimizing all aspects of the robot, including the body, in an environment is particularly crucial if we want to have this kind of emergent simplification phenomenon. But why dealing with soft robots in particular? Well, because there are some evidence of the fact that a soft body can facilitate the emergence of this kind of phenomenon, as it provides a better mean of interaction with, between the brain and the environment, in the form, for example, of richer proprioceptive and exteroceptive stimulation, and also greater computational power. So in the following, we're going to evolve soft robots in particular. So you have seen this already quite a few times, but basically, just to sum up our approach, we have in mind this comprehensive bottom-up approach that relies on evolution. On top of evolution, we can also start incorporating developmental dynamics, and we'll see some examples of that later on. In this case, we talk about evo-devo because we have development that is kind of developmental trajectories are kind of fine-tuned by evolution. And on top of that, we see the sensory motor dynamics, so the short-term time scale, the here and now. All right, so we're gonna deal with some case studies in this evo-devo sort of field, so evolutionary development of soft robotics. First, we're gonna see a very engineering application of this kind of techniques. So we're gonna use evolutionary algorithms to solve complex optimization problems. Later, we're going to present an example of using these kind of techniques in order to explore the design space of a robot, to study specific properties of animals, and also to perform broader investigations, such as studying the evolution of soft locomotion, free-form evolution of soft locomotion, and the evolution of development and morphological computation. So, as for solving complex optimization problems with evolutionary algorithms, some time ago we happened to work on a project related to this pose-drone robot. This is a soft octopus-inspired underwater drone, and we had a dynamics model of its locomotion. We wanted to use this model in order to improve the robot, and particularly to identify faster gaits for the robot. The problem was that the model struggled to describe the behavior of the robot, and that was due to the many unknown model parameters. So what we did was to try and apply evolutionary algorithms in order to ground this model into the physical reality through a parameters estimation procedure that was not solved through conventional techniques. And basically the problem was formulated as an optimization problem, where the goal was to find a set of unknown model parameters that happen to minimize the model to robot discrepancies. And this was solved through genetic algorithms. So this is a very straightforward case study in which we just use genetic algorithms as a tool, just to give you a sense of what we can do with this kind of techniques, also in the engineering domain. So after we performed this procedure, the model was actually able to faithfully represent the overall dynamics of the robot, and as a consequence, we started using it in order to improve the robot itself. Here you see the comparison between the trajectories of the model and the robot, and you see that we now have a good match between the two, so we can use the model to predict the behavior of the real robot, which we did. And for example, we happen to identify faster morphological configurations for the open loop locomotion of this robot, and some of them, as you see in the bottom right corner, happen to transfer to the real world, entailing considerable performance increase. And also we use this the model in order to explore in simulation the viability of paradigms of adaptive morphology or morphosis. The next application, we tried to generalize upon this model, and the goal was to perform a more extensive exploration of the design space of the robot. So what we did was to generalize the model and feed it into a more general evolutionary system. Particularly, we used a novelty-based evolutionary algorithm in order to explore the design space. that is an algorithm, a genetic algorithm, in which instead of rewarding individuals that perform better, we reward individuals performing differently. And this actually favors exploration of the design space, which is what we wanted. We found some interesting results in terms of embodiment, for example, and particularly we observed that artificial evolution was able to systematically exploit and discover embodiment in the form of carefully tuned dynamic interplays between morphology, control, and environment. So this was nice. And also we were interested in seeing whether artificial evolution could provide design indication to the human designers. So for example, for this robot, the basic morphological arrangement that was featured in the model was designed by humans in order for the robot to crawl on the seabed. But actually, artificial evolution suggested very different locomotion modality that turned out to be much more effective. That is to have these kind of very fast strokes of the limbs in order to have the so-called sculling-based swimming. So the robot started swimming away from the seabed instead of crawling, which is what we expected. And the way artificial evolution did that is also interesting. It did so by reinterpreting or exapting human-devised solutions originally conceived for different purposes, which is something that evolution usually does. Evolution is kind of lazy. So instead of reinventing things from scratch, if there is something that can be reinterpreted and adapted to a new purpose, evolution will try to do that first. And this is a notion that we can call artificial creativity, if you like. Okay, this one is nice because it actually started as a cone for the Shanghai Lecture 2014 and is another application of evolutionary algorithms in which we try to study something related to a biological model. The goal here was to study the embodied intelligence of fishes such as the manta ray as a paradigm for underwater soft robotics. And also we were interested in studying the relevant factors for the adaptation of this kind of morphology to different fluids. So what we did here was to develop a simple simulated model for a compliant manta-inspired fin, and then to co-evolve the morphology and the control of this robot in different fluids. The fitness function being based on fluid dynamics metrics associated with swimming efficiency from the biological literature. And not going to enter into the details, but here you see the results of this study. I mean, this simulated compliant wing forming in this virtual environment, and you can sort of guess that the behavior is kind of I mean, it resembles the one of the biological model, and also quantitative metrics indicated that the results were consistent with the biological system. And we did that for a couple of different environments and understood what are the most important factors for adapting this kind of morphology to different fluids. Here we move towards more general evolutionary systems, and the first things we started to do was to study the evolution of soft locomotion with these tools. So particularly, we wanted to investigate the free-form evolution of soft locomotion in both aquatic and terrestrial environment. Free-form in the sense that we don't want to work on a model that is already pre-shaped by humans, but we want to start from a blank workspace, both for morphology and controller, and we want evolution to figure out how to assemble robots using some material in order to have effective locomotion. We were also interested into studying the effects of different material properties on the evolved morphologies, behaviors, and energy performance trade-offs. And finally, we wanted to study the effects of environmental transitions from water to land and then the other way around on the evolution of locomotion. So questions such as, is there any benefit in evolving swimming locomotion first in order to later evolve walking, and the other way around? So this setup was based on a powerful soft robot simulator, which is called VoxCat, on a multi-objective evolutionary algorithm, and on a powerful developmental encoding, which is known as CPPN. I think Josh touched on this in his lecture. So in the optimization, we asked to maximize travel distance, minimize the muscles being present in the robot, so the energy, if you like, and minimize the employed material. And we did experiments both on land and in water by providing 5 different materials to evolution, characterized by 5 different stiffness values, S1 being the softest and S5 being the stiffest. And then we also did these transition experiments that I mentioned before. So we start evolution on land, for example, and then halfway during evolution, we move the whole population in water, or the other way around. And what we saw is that on land, the terrestrial locomotion cannot be evolved if the provided material is too soft, which is intuitive. If you take an octopus and you put it on land, it's not able to locomote very well. And as we move towards more stiff robots, we observed better performances and lower energy consumption, and also an increase in morphological and behavioral complexity. So on land, soft robots are simpler robots and they are simpler morphologies and they perform simpler locomotion, such as inching and crawling. But as we provided a more stiff material to evolution, we happen to see more complex morphologies and more coordinated gaits being produced, such as this one that you see over here. This is a robot that was evolved, but the morphology and the control are evolved from scratch, starting from a blank workspace. This green propagating wave is the actuation signal that was evolved too. And you see that this robot is happen to locomote pretty well on land. Things are a little bit different in water, and this stresses the relationship between the morphology and the environment in this case. In this case, we observe more complex energy performance trade-offs, and particularly we found out that softness was more useful in water than it is on land. And we evolved a bunch of different robots, such as this one, which resembles a jellyfish, if you like, and others, such as this one. It is not very different from our previous Manta robot, if you like. Regarding the transition experiments, we observed an asymmetry. And particularly, we observed that evolving terrestrial locomotion first didn't help and actually was harmful in order to later evolve swimming, whereas evolving aquatic locomotion first seems to help in later evolving terrestrial locomotion. And for example, doing this kind of analysis, we also happen to observe other interesting phenomena, exaptation phenomena, as we commented before. For example, when moving from land to water, robots develop flapping appendages for swimming, whereas when we move it from water to land, those appendages are usually lost and are adapted and shortened in order to become legs or arms. And here you see some example of this kind of exaptation. This is a robot on water and becomes something different if we move it on land. A jellyfish like this one becomes, after further evolution, a hopping robot like this one on land. Or maybe this other jellyfish here adapts its flapping appendages in order to perform some kind of terrestrial locomotion. And we can study also the reverse. So when moving from land to water, a quadruped like this one is going to grow some tentacles in order to better locomote in water. Yeah, this one. So you see this property of evolution trying to readapt previously discovered solution to a new purpose, which is something that happens in biology too. So it's nice to observe this in an artificial system as well. And actually, the fastest terrestrial runner that we see here in slow motion was the result of this two-stage evolution. So it used to be a robot that performed aquatic locomotion, and you also see some traces of ancestral tentacles at the top that were used for swimming, and now they are adapted and they provide a balance to the robot. So if we remove these ancestral tentacles, actually the robot is not able to locomote anymore. And the last application scenario is related to the study of development and morphological computation, particularly the evolution of development and morphological computation. But morphological development is pervasive in nature, and soft robots have a largely unexplored potential in this respect. So we started doing this kind of investigation because we think that simulation studies can help understanding these new abilities in such a way that we can better harness them. Oh, I think there is music here. Okay, so what we did here was to start evolving robots that could grow. And the first task that we provided to evolution was phototropism, so growing towards different light sources present in the environment. And on top of evolution, we started modeling time-dependent environment-mediated developmental dynamics. And in this case, we talk about volumetric changes of every little piece of material, which is called voxel, volumetric changes in response to the sensed light levels. So evolution could decide to employ blue pieces of materials that shrink when they're close to the light source, or red pieces of material that actually expand when they're close to a light source. And what evolution optimizes is both the morphology and the developmental parameters. So for the topology and the developmental properties of every piece of material. Here you see some of the evolved creatures, and developmental time unfolds from top to bottom. And you see that all of them try to reach out towards light sources that are not depicted here, but they kind of grow and unfold from a early stage to an adult form in the last stage of the evolution of the development. Sorry. And at this point, having this setup, we start asking more questions, such as under which conditions does morphological computation evolve in this kind of growing soft-bodied creatures? And what we observed here is something interesting, that is that material properties influence a lot evolution's ability to find effective morphologies. So when material properties are suitable, evolved creatures exhibited more effective and natural behaviors, better exploited the interaction with the environment, and leveraged passive dynamics in place of active control, which is what we intuitively associate to morphological computation. And here you see two examples. This is a soft robot that is asked to point towards those two yellow boxes on the sides, and you see how the robot passively unfolds under the effect of gravity and achieves this nice curvature that allows it to point toward the light sources. Developmental control here is very simple, it's just expand. But what happens if we provide evolution with a stiffer materials that is not very suitable for this specific task environment? Well, what happens is that evolution has harder times in producing an effective robot and comes up with a fully actuated robot like this one that is not actually exploiting the environment, it is fighting the environment, laterally reaching towards the light sources. And you see more colors appearing here because the developmental control has to be more complex. We needed some kind of antagonistic action in order to solve the task. And we also quantified this in information theoretic terms. So what we showed is that in this specific task environment, software robots perform better despite using simpler growth controllers. And the complexity of the growth controller was computed in information theoretic terms, so by using basically Shannon entropy. And so this is a way of quantifying morphological computation in this specific domain. And what we also observed is that when morphological computation could not be evolved, as in the case of stiff robots, evolution automatically tried to compensate for it by complexifying the control, which is something that we might want. So in a sense, the soft robots that was passively unfolding toward the light sources is something that might resemble the passive dynamic warfare that we probably saw in the lecture. So a robot that in presence of very simple control is able to solve a complex task by exploiting morphological computation. Whereas the second type of robot, the stiff one that was fighting against gravity, can resemble a fully actuated robot that doesn't exploit the environment, the interaction with the environment so much. The last question that we asked was when and how, and in response to which stimuli should the soft-bodied creatures adapt? And this is something very interesting because we know that soft robots can adapt, but how should they adapt? If we want to exploit their new abilities, we need to understand that. And also we wanted to understand whether evolving morphological development could result in increased adaptivity and robustness. So in this case, again, we resorted to a locomotion task, and here evolution dictates the stiffness of each piece of material, the initial stiffness, but also it dictates whether a voxel should soften or stiffen in response to mechanical stimulation. And this is inspired by biology, concepts such as the Wolff's law of bone remodeling. So we have material that can alter its properties based on the interaction with the environment. And it does so along a developmental time scale. And also evolution could automatically decide which sensory stimuli should drive this adaptive change. It could choose between internal stress in the material and internal pressure. So what you see here is one of the best robots that we evolved, that has evolved the strategy in which it stiffens the parts of the body that are repeatedly stimulated. And you see the red pieces of material here, they are becoming red because they interact more with the environment, so they stiffen. What happens is that at some point, we change the environment, and particularly with double gravity. And that you see the robot at first is stuck because it never saw this environment. But you see that the color change here, and this sort of red skeleton grows all around the robot. So a change in the environment triggered a different sensory stimulation and a different adaptation. And this red skeleton that you see here happens to help a lot locomotion. So the robot becomes able to better withstand gravity and to regain as much as 40% of its original fitness in an environment that it never saw. So basically, it appears that the evolved adaptive law is general enough and could result in an increased adaptivity and robustness. So coming to the conclusions, what we try to show is that artificial evolutionary and developmental approaches can solve complex engineering problems. They can represent a general and comprehensive framework to automatically design adaptive robots for arbitrary tasks and environments. And this is promising because with progresses in software fabrication and 3D printing, we can envision a fully automated design, fabrication, and deployment pipeline. Also, these techniques can inform soft robotics and can help us unleashing its full potential, especially in terms of adaptivity. But more than anything, these techniques can help understanding the conditions under which adaptive and intelligent behavior emerge in biological and artificial systems. Some other remarks from the work that we have presented: the notion of evolutionary creativity, the fact that artificial evolution is able to somehow think outside the box and can suggest effective and counterintuitive solutions, the fact that it can systematically produce embodiment and morphological computation, and additional remarks on the importance of the body, and particularly material properties, which can dramatically affect the emergence of different morphology and behaviors, as well as morphological computation. And finally, the idea that artificial evolution can discover automatically adaptation laws for soft robots that can result in increased robustness and adaptivity. So I would like to thank you for your attention, and if there are any questions, I will be happy to receive them.
Okay, thank you. Thank you for your very interesting and inspired talk.
Thank you.
So if there are questions, we are a bit late with schedule, but if there are questions, I think that Francesco will be happy to take them. So use the chat to book your question, if you have one. Okay, since it's probably late, but Francesco and me will be happy to, so I will be happy to put you in contact with Francesco, or be free to feel free to contact him directly. And so see you next Thursday, where we will actually discuss about mathematical modeling of morphological computation. So thank you again, in particular to the Asian people sticking until a late hour, and see you next time. Thank you, Francesco, again for accepting our invitation. Thank you, everybody, for attending. Bye-bye.
Thanks for having me. Bye.
Bye-bye.